Hi there. Welcome back. I'm Quillen, and I'm glad that you've decided to continue on this journey with me of calculus. Today, we're going to be talking about a topic that you may have covered in your pre-calculus course, although for many students that is not the case, and that's completely fine. Today, we are talking about limits. Limits are very important to understand conceptually and graphically, and then also operationally as you start moving into true calculus topics, especially the derivative. The limit is the value that a function approaches as the independent or manipulated variable. Usually it's going to be x, although it also might be u or v very commonly, gets closer to a specified value. And that's infinitely close without quite reaching it. And we will talk more about that either towards the end of this video or in the next video, depending on our time. So it will be most helpful to start thinking about this graphically before we move into non-graphical interpretations. So I've prepared this graph on Desmos. Let me zoom out just a bit so the numbers are a little less awkward. And this is, as you can see over here, the graph of f of x equals x minus 1. And I do suggest that you get used to using the f of x notation instead of the y notation, because it will be really, really important to understand the relationship between f of x and x as we start moving forward. So let's say that we want to find the value of f of x at 2. Well, we can just look at the graph. If you look over here, right at x equals 2, you go up until you find the line, and that is at y equals 1. And I'm sure that you know how to do that. That's a very basic Algebra 1 level skill. And you can check on Desmos by tracing along the line to the point you want, and you will find that indeed x equals 2 means that y, or f of x, equals 1. Having some trouble maintaining it there, but you see the idea. I'm going to try and move my cursor out of the way so you can see it a little better right there. Now, what if we want to find the limit as x approaches 2, so as x gets infinitely, infinitely close to 2? What if we want to find the limit as x approaches 2 of this function x equals 1? Well, we have to go from both sides because we haven't specified which side we're coming from. And that's just a rule of what a limit is. So going from the right side, going from the left side rather, the negative side, let's trace starting at x equals 1. So we're tracing, and it's not agreeing with me. So we're tracing, and we're tracing, and we're getting closer and closer to x equals 2. It looks like that number is approaching 1. And of course, we know that it truly is approaching 1. Let's try it again coming from above. Let's start at x equals 3, y equals 2. So we're tracing down and down and down. And as that x value, your first value, is getting closer and closer to 2, it looks like that y value is still getting closer and closer and closer to 1. And we can zoom in and check that even if we come from 1.9 instead of 1, and we trace up there, it looks like it's getting close to 1 as we get close to 2. And the same thing it happens if we come from the right side. So, based on this, you might conclude understanding the limit really isn't super important because it's just the same as evaluating a function. And at the most basic level, it really is. But sometimes you'll have a special case, and these special cases come up a lot when you start dealing with fractions and exponents especially. Sometimes you'll have a special case where the limit exists even though the value of a function at that specific value does not exist. And that's even though the output at that specific input may not exist for that function. So let's look at a mostly identical function. F of x equals the quantity x squared minus 4x plus 4 all over the quantity x minus 2 plus 1, which is the fancy way of saying this function. And you'll notice that graphically, it looks exactly the same. And if you simplify this fraction, it'll simplify down to x minus 2, and then adding 1 to that, it'll simplify as a whole to x minus 1. So graphically and numerically, it is almost identical. But you may note that, and I hope that you do know, that 0 in the denominator of a fraction is undefined. You cannot work with it in algebra. That remains true for calculus. 0 in the denominator means that it's not a number. And so it is inconclusive to say that the value of a function is something over 0 is not really correct. The value would be undefined. But a very interesting fact about this is that it only is true of that one point. So looking at this, it seems like it's completely continuous. It never has any breaks or gaps. But we know that there's a hole here. If we zoom in, we can zoom infinitely far in and never, ever, ever get to any point where this looks like it has a hole in it, because that hole is infinitely tiny. So what then can we do to identify that value if we can't ever zoom in and see what it looks like it would be? Well, we can use the limit to see what that value approaches. And just like it sounds, we're going to approach that value from both sides. So let's start by approaching from the left side, the negative side. We trace this line. Sorry, I clicked the wrong value. Let's start from the left side. We're tracing along the line, and it looks like we're approaching 1, even though right there it is truly undefined. But as we get closer and closer and closer, it's getting to 1. Let's try it from above, see if it's the same thing. So we're coming in from above, tracing. It looks like as we get really close to 2, that value is getting really close to 1. Right? Let's zoom in and see if that stays the same. So coming from 1.9, tracing. We are super duper close to 2, and that value is super duper close to 1. And as we get closer to 2, that value is getting even closer to 1. But it's undefined. Let's come from above. Same thing, just tracing. And as we get super duper close to 2, that value gets super duper close to 1, even though it never quite gets to that 1. It's undefined. That means that the limit as this function over here approaches 2 is 1. The limit of this function as x approaches 2 equals 1. And there's a very specific way that we would write this. Let's move back over to the whiteboard and check that out. So the function looks like this. My handwriting is not great. I apologize for that. But I'm sure that you can glean just enough from it. So lim, and then under that notation lim, you write your independent variable, usually x. So let's call it x for now. As x approaches. And what number do we care about x getting infinitely close to? Well, we care about it getting infinitely close to 2 because that's where our hole is. So we need the limit to figure out what it should be. So as x approaches 2 of, and you can do this with or without brackets if it's one term, but since we have more than one term, we have this plus 1 out here. We do need to use brackets, and it's almost always going to be regular standard parenthesis brackets as x squared minus 4x plus 4 whoopsie, that was the wrong stroke, over x minus 2 let me erase that, right? Whoopsie. X minus 2 plus 1 to all that equals 1. And then you can circle this answer, or you can put a box around it. But we aren't really turning this in, so you don't need to box or circle your answer. But this is what the notation looks like. It is the word, or it's the abbreviation lim with variable, arrow. This arrow always points the same direction. Number or value that you want it to get really close to. Sometimes it'll be a non-value, but for now, just it's a value. So input variable approaches a number, and then I would recommend always using brackets. That way your notation is always completely understandable. Whoever is reading it, including possibly future you, knows exactly what you meant, and there's no possible ambiguity whatsoever. And then you just set it equal to the solution, just like you would any other operation. So let's do a really quick review, and then I will pause, provide you with some examples, and we'll come back and talk through. So a really quick review is, in a lot of cases where you have a graph, you can just trace along it and visually tell what the limit of a function at a certain value is, even if you know, such as in this case, that that function is undefined at that specific variable. However, it does need to approach the same value from both directions. There are cases where this is not the case, but you should, for now, always be looking at limits that come in from both directions. So I'm going to pause, put some examples on screen, and then come back and we can go over them. All right, welcome back. Here are your two examples. They are in blue. The first example has a red graph. The second example has a yellow graph. Now I will move to the next slide so you can see what these graphs are. However, I will give you a moment to write down these problems. All right, so again, that first problem is represented by the red line. The graph in question is graphed in red, I should say. And the second problem has a function which is graphed in yellow. Take a moment and try to figure out the answer for yourself. I will tell you the answer in 3, 2, 1. All right, I hope you paused and had some time to figure out the problem for yourself. Let's take a look back at the questions being asked. So the red line, as it approaches 1, what is the value there? Well, it doesn't look like there's a hole or anything. It looks like it's just completely normal, so we can view the graph at 1 and trace up. It looks like at x equals 1, the graph of the red line is at 3. So that means the limit at that value of f of x is 3. That's a little big. I didn't realize it was going to be that big. But there's your answer. Now let's look at the yellow. So we are looking at the limit as u approaches 2. So u is going to be equal to 2 right here on this vertical. So, well, coming from the left, it looks like that value approaches 0. But if we come from the right, it very clearly does not approach 0. That might be more like 6 or maybe 7. So because it approaches different values from both sides, and remember, it does have to approach the same value for it to be a true regular plane limit. This means that the limit of u as u approaches 2 of the function g of u, specifically talking about this yellow line, does not exist. And you represent that by writing d in e. And again, remember, I have bad handwriting. Yours will likely be cleaner looking than this and more legible. So I hope that this has been a helpful review or maybe preview of the idea of a limit. In the next video, we will talk about one-handed limits and maybe some other surprise topics. I hope you come back and find out. Thank you for joining me, and thank you for continuing with me on this journey through calculus. This is Quillen signing off.